Now let's look at the chain rule with more than one independent variable. Let's say we have W is a function of X, Y, and Z. Then when we construct the tree diagram, we'll have W at the top node, and we'll have an X, a Y, and a Z on that next level. So we have W depends on X, on Y, and on Z. Now, in this example, we have that X is also a function of T. So X is some G of T, or sometimes you'll write it as X of T, and Y is some function of T, so H of T, and Z is some function of T. So X, Y, and Z depend solely on the variable T. So we'll just have T coming off of each one of those. So now, label each of the branches in your tree diagram with the derivatives associated with those branches. So we know that W depends on X, Y, and Z. So if we take the derivative of W, it will be with respect to just one of those. So it'll have to be a partial derivative. So this first branch will be the partial of W with respect to X. This one is the partial of W with respect to Y. And this one, the partial of W with respect to Z. So now, each of these other branches, since X, Y, and Z have just one independent variable that they depend on, then we just use the regular derivative, dx dt, dy dt, and dz dt, respectively. So now, to find dy dt, three different parts will contribute to dy dt. So take the paths that end with the t. We have path 1, we have path 2, and we have path 3. The contributions to that change in W with respect to T come from the change, the partial of W with respect to X times the derivative of X with respect to T. The partial with respect to W of W with respect to Y times dy dt. And the partial of W with respect to Z times dz dt. So those are the three rates of change that contribute to the overall change in W with respect to T. So there's our chain rule. When we have several, we have the one independent variable T, but we have the several intermediate variables, X, Y, and Z. Okay, so now there's so many variations of this chain rule, so that's why we want to use the tree diagram to be able to quickly get a chain rule for that particular situation. So don't try to memorize these formulas, just know how to get them from the tree diagrams. So in this problem, we're told that Z is a differentiable function of X and Y. So we have Z here with X and Y off of that. X, Y are differentiable functions of S and T. So now we have more than one independent variable. So X depends on S and depends on T, and Y also depends on S and T. So we'll have S and T at that next level under both X and Y. Identify each branch. This first one, since we have two variables at this level, there'll be partial derivatives. So the partial of Z with respect to X and the partial of Z with respect to Y. And now these branches, because there are two independent variables for X, it's the partial of X with respect to S and the partial of X with respect to T. Likewise, the partial of Y with respect to S, the partial of Y with respect to T. So now, if we want the partial of Z with respect to S, look at the branches ending with S and take the paths that contribute to that. So the change in X with respect to X of Z with respect to X times the derivative of X with respect to S, plus the partial of Z with respect to Y times the partial of Y with respect to S. Those are the only things that contribute to the change in Z with respect to S. So now, let's say we want to find the partial of Z with respect to T. Look at the paths ending in T, take the whole paths that end at that T value, the partial of Z with respect to X times the partial of X with respect to T. and then the partial of z with respect to y times the partial of y with respect to t. And that's the chain rule, finding the derivative, the partial of z with respect to t. Since there were two independent variables, we'll have partials of z for each of those. So now z is given by this function, and from that I can conclude that z is a function of x and y. But x is a function of s and t. And y is a function of s and t. So there's our tree diagram. Go ahead and label the branches. This is the partial of z with respect to x because there's two independent variables of z, and the partial of z with respect to y. And here we have the partial of x with respect to s, since s and t are two independent variables, and the partial of x with respect to t, the partial of y with respect to s, and the partial of y with respect to t. So the partial of z with respect to s, look at the branches ending with s, and take the two paths associated with those. So we have the partial of z with respect to x times the partial of x with respect to s plus the partial of z with respect to y times the partial of y with respect to s. The partial of z with respect to t, we'll take these two paths. So we have the partial of z with respect to x times the partial of x with respect to t plus the partial of z with respect to y times the partial of y with respect to t. Now let's fill in each of those partial derivatives. The partial of z with respect to x, cosine of 3y is a constant, so we'll have cosine of 3y times the derivative of sine of 2x, which will be cosine of 2x times 2. So that's the partial of z with respect to x. The partial of x with respect to s will be 1. The partial of z with respect to y, sine of 2x will be a constant. The derivative of cosine of 3y will be negative sine of 3y times 3. And now the partial of y with respect to s will be just 1. So we have 2 cosine of 3y cosine of 2x minus 3 sine of 3y sine of 2x. Now, if you want to leave this in terms of s's and t's, the independent variable, we can change the x's and y's over to s's and t's. So might leave this as the partial of z with respect to s equal, I'm just going to change the y and the x here using these two equations. I'm going to have 2 cosine of 3 times the y, cosine of 2 times the x, minus 3 times sine 3 times the y, sine of 2 times the x. Okay, now the second problem. We want the partial of z with respect to x, which we already found up here. We don't have to re-find it. That's 2 cosine 3y cosine 2x times the partial of x with respect to t is 1, plus the partial of z with respect to y, which we found that right here, is minus 3 sine 2x sine 3y, times the partial of z with respect to t, y with respect to t is negative 1. Okay, so simplifying, we will have partial of z with respect to t equal 2 cosine of 3y cosine of 2x plus 3 sine 2x sine of 3y. Let w be a function of x, y, and z, each of which is a function of s and t. So w, you could write it as w is a function of x, y, and z, or just go to the tree diagram. Each is a function of s and t. So you may have x is equal to x of st. You don't have to change the function name. That sometimes they just use the x and the y. That way they don't have to use various other variables. So this is one way to write their functions of s and t. Draw the labeled tree diagram showing the relationships. So we've got that. Now we just need to label the branches. So we have a partial of w with respect to x, since we have 3 variables at that point. Partials of x with respect to s and t. Partials of y with respect to s and t. Okay, write the chain rule formula for the partial of w with respect to s. Well, find the branches ending with s and take the paths leading to that. So the partial of w with respect to s, we'll have the partial of w with respect to x times the partial of x with respect to s plus the partial of w with respect to y times the partial of y with respect to s plus the partial of w with respect to z times the partial of z with respect to s.